Hi, this is a voiceover for attempt two. So this is the planetary system testing for the gravitational attraction and the just gravity between planetary system in general. So we're going to first test the orbit. We're going to track the object, the closest nearest object to the sun, which is the Mercury, because it travels fastest, so the weight the least amount. I'm sorry about that. So we're going to test out the time control very soon as well, as we're going to use the time control to limit the amount of time that we're going to waste here just staring at the screen for no reason. So, as you can see, the really tiny dot just below the sun, that's Mercury. I pointed an extra marker in the Word document for those who have struggled to find it. You should be able to. So we're just gonna wait for it to move. You can see the sun is having a slight movement as well. Don't worry, that's because of the floating origin system. So that's also being tested here. That's being correct due to the spaceship not being completely still, but being gravitationally attracted by other bodies as well. It also updates position, so therefore the sun also updates its relative position as the spaceship's always centered in 0, 0, 0. You can kind of see how Mercury is also traveling way quicker than our planets out orbit, and a planet with greater radius has a slower travel speed, which is true as if the as the as that's how GMM over R squared works. So for M equals mv squared over R, so that's how centripetal force would work as is proportional to R squared. So here, you just saw the Mercury complete one orbit, and it's roughly circular. So I'll consider that as a successful objective. We've also tested the time control and also a bit of floating origin system. You see more clearly in the next test. In this test, we're going to test for um, v- um, Earth, Saturn, and Venus, I believe. And this is to place a body really near to the planet and to test its gravitational attraction and its movement towards it. So we're going to start with Earth. We're going to make spaceship 101 units away from it. The reason for this is 100 units is where the scale changes. So I don't want to break my system. And I just want that to be as close as possible so that I have the greatest gravitational attraction. As you see in a second, due to that, not every single time the spaceship gate landed on the planet, the attraction is not as strong, since the planet is also orbiting around the sun with a relatively high velocity. We're going to test the time control using the time control command again to show that it works. And as well as we need to just speed up this experiment so that this video won't take 14 hours or 14 days. But as you can see, the Earth is being rotated. There's also much flatter movement compared to what we consider in a perfectly circular orbit. So therefore, it's tested correctly. Although you can say this is also due to the sun's movement as well, or the sun's relative movement to the spaceship as it is being accelerated towards the spaceship. Next, we're going to test Venus. Venus should be pretty similar to Earth since it didn't attract Earth. It should also attract Venus since the mass of it is pretty similar. And if the mathematics of it is correct, it should give a similar result. So that's for the second test. You can kind of see Venus just underneath the red arrow there. I'm just speeding up time of simulation. Although it must be said with a bit of caution that time of simulation, if added too much over time, it would cause a chaotic system, as in the numerical system. Even RK4 has limitations. But for this experiment, it should be alright. As you can see, it's similar trend to Earth, which is the orb is much more flat, but it doesn't get attracted into the spaceship. And you see the sun coming up in just a moment. There you go. Due to the floating origin system. So that's also working again. So now for the last test, we're going to test Saturn. I'll click on it in just a second. The science should have much higher mass, so therefore it should be attracted towards the spaceship, as in the spaceship should be attracted towards the planet, or the other way around. But it's relative motion, so I can't really actually spot which way is it, as it is from the spaceship's point of view as the origin. So technically, on the frame, it would appear as if the planet is moving towards the spaceship. In reality, it is the spaceship getting attracted into the planet. Starting simulation now, and wait for it, and wait for it. And here we are. I just forgot that the position I said was wrong, and I almost screwed up my system. So luckily, I did remember. I also didn't set it to exactly 101 units away because I just want to show that even a slightly large distance away, probably even larger than what I've said, it would still get attracted to the planet since it's just so heavy. So it's G, it's proportional as the G, small g, as in the acceleration is proportional to the mass of the planet. And that creates a mass around 1,000 times. Actually, not 1,000 times, only 100 times, but 100 times quite a bit still. Then you see it should also be 100 times as strong a force exerted on it, so therefore the attraction is much greater. You can also see Saturn has a much greater radius compared to the rest of it, which makes sense, as it's a much larger planet. You can see the scale change working here as well. We just landed on it. So that, I think, that concludes the test for now. Thank you very much. And you can check back on the objectives. We have completed most of it. For you see, we'll be testing this further video as well. But here we are. Thank you.